The key to making sense of these electrophilic substitutions is to learn a little bit about this intermediate that forms along the way. This is representing the first step of really any of these electrophilic reactions in which we create a carbocation with one of the carbons in the ring. Now the E here stands for the word electrophile. It doesn't stand for an individual element whose symbol is E. If this were the nitric acid reaction, that first one there, then that E would actually be this nitro group. So E sometimes is a group of atoms. This is how nitric acid is put together, and so this bond is broken to create a hydroxide on the right side and leave behind an NO2 group that does have this positive charge to it. And that positive charge is the key to getting these electrons in the ring to form a new bond. And so over here on the right side, that E would be a NO2 group if we're using nitric acid. And it's the stability of this carbocation that allows that to happen. Now they're not showing the final step in the process, which is to reform the double bond that was broken here in this step. But when we reform that double bond, we're going to do it using these electrons connecting the carbon to the hydrogen. So that way our electrophile stays on the ring, and what we get is a benzene ring that has its familiar 3 double bonds, but now has a NO2 group in place of that hydrogen. And in this example, that hydrogen would be associated with the OH group, and we'd create a water molecule as a byproduct. All of the electrophiles are working on a similar principle. If we were doing this with Br2, we'd have 2 bromines that are covalently bonded, and in that reaction you'll notice they mention FeBr3 over the arrow. That's a catalyst. This is the iron bromide catalyst. And what it does is make a new bond here to one of the bromines, which causes the bromines to let go of each other. And that creates a relatively positive bromine and one more negative as those electrons shift. And it's that bromine with positive charge that behaves the way the NO2 group does. And so we get a bromine on the ring. In the examples that involve the Friedel-Crafts alkylation, that involves starting with an alkyl halide, such as the one they show on that previous slide, the tertiary butyl chloride. But that chloride is removed to create the corresponding tertiary butyl carbocation, and that becomes the electrophile in that case. And oftentimes whatever is removed to create that electrophile, to create that positive charge, it involves atoms that again end up as part of that byproduct down here. But whether a electrophilic substitution happens, how fast it happens, greatly depends on how stable this carbocation is that we create. And we'll see that if you have other substituents already on the ring when you attempt such a substitution, that can greatly affect the rate at which those substitutions reactions happen. If you have something other than just hydrogens on this benzene ring, sometimes the reactions are faster. On other occasions they are much slower, even if they can be accomplished. But this is just a good general way to think about what's going on when we talk about what an electrophile is all about and how it goes about switching out with one of the hydrogens in that ring.